Ladies and gentlemen, today we will talking about the solving Lorenz ordinary differential equation system based hardware poster in 19th International Conference on Intelligent System Design and Application by Hassan Al Yassin, Muhammad Abdurrahim Fadl, Omran Al-Shamma, Laith Al-Zubaydi from the University of Information Technology and Communication, Baghdad, Iraq, and Faculty of Science and Engineering, Queensland University of Technology, Brisbane, Australia. The aim and objective. This paper will focus on the applied Lorenz system by using hardware accelerator to take advantage of the parallel architecture. Introduction. Edward Lorenz is the first person who studied the Lorenz system. A set of the chaotic solution of this system is called the Lorenz attractor. These attractors look like a butterfly, like this figure. Lorenz considered various chaotic systems. He introduced a convective flow problem in 1963. In 2D fluid cell, which heat up from the bottom and cool down from the top, generates convection. It can be represented using only one partial differential equation. This equation, as shown in this slide, from equation 1 to 3 represent the Lorenz equation. The x value called the convection over tuning rate. X and y is the variation of the horizontal temperature and vertical temperature. Alpha is the ratio of the fluid viscosity to the thermal conductivity. R is proportional to the Rayleigh number and the parameter. B is dependent on cell geometry. The hardware implementation. As mentioned earlier, the goal of this paper is applying the Lorenz system by using the hardware accelerator called Altera DE1 system on chip development board using MATLAB language release 2019 summoning software. First step, the Lorenz subsystem was the download to the FPGA. The remaining block formed a part of user interface and ran in Simulink. The initial value of the variable called z, y, and x. So this equation is for the Lorenz system are regenerate to avoid the overflow. To create the model, the right hand side of the above equation were implemented in the block level using adder and multiplier. The resultant equation were fed to an accumulator block. The output of the accumulator were fed to the unit delay block. The delayed output are fed back as input to block to be used for calculation in the next cycle. The next figure will equate this to the register and transfer level model to generate from benchmark Verilog design. This figure are the Lorenz system in the HDL language. The result and discussion. In the first step, we must verifying the correction of the Simulink model. To do this, the model was simulated in normal mode without HDL generation. The output waveform were verified on time scope. The parameters were verified and the effect of variation was observed on the scopes. As I mentioned earlier, we must compare our work to the different platform, like the CPU. The CPU are compared to the FPGA with respect to the time execution. Finally, we conclude the FPGA design has lower time calculation than the CPU, taking into the mind that MATLAB language is not quickest language. This paper are displayed the different figure with a different parameter, then calculate the time in second by the CPU and the time in millisecond by the FPGA. Figure A, figure 5A to the 5H are also displayed in the next slide. This is the different Lorenz system figure with a different parameter. Conclusion: the Lorenz ordinary differential equation system was completely designed in Simulink. The design was tested in both simulation and after synthesis with the FPGA in the loop. This paper was a huge learning experience through the learning curve was high. Even though the Lorenz system is a relatively easier system, the experience gained from implementing the system was significant. In addition, we verified the Lorenz solver system of the different platform in which to calculate the time of execution of various wave from depending on the alpha R B values. Finally, thank you for listening and see you again.